So electrostatic potential and capacitance. So we have seen the introduction of electrostatic potential. So the meaning of electrostatic potential, we have discussed about that. So the potential or potential difference, electrostatic potential or electrostatic potential difference is basically defined as the electric potential. So this potential and potential difference, these topics should be spoken where we have an electric field. Where we have an electric field, in that area only we can speak about what is the potential at this point, or what is the potential difference between these 2 points. So if there is an electric field, so there is a force field. Electric field is nothing but a field of force. So in that field of force, if you bring a 1 coulomb charge, so work done to bring 1 coulomb charge from infinity to, from outside to that particular point. Infinity to that point is called as electric potential at that point. So this we can see electric potential at that point. And if you want to know about the potential difference, that is the work done to move electric potential against electric field. That is the important word, against electric field. So work done to move 1 coulomb positive charge from infinity to that point against electric field is called as electric potential at that point. Electric potential at that point. So basically, if we have a charge Q, capital Q, so surrounding to this plus Q, we have an electric field. If you want to find an electric potential, let it be at point P. So we need to bring 1 coulomb positive charge from infinity to this point. Let the position of this capital Q will be O, and the position of the plus 1 coulomb is P. So the distance between, if the distance between Q and P is considered as the R, let the distance between the source charge and the point charge, if it is considered as R, then the electric potential can be defined as, to move a small distance dr, the amount of work done. To move a small distance dr, the amount of work done to bring 1 coulomb charge is equal to, we know the formula for work done. Work is equal to force into displacement. So here basically we are doing work to bring 1 coulomb charge. So basically what we are doing, we are trying to find the work done per unit charge. So that is force per unit charge into displacement. So in that I explained that this force is varying with respect to displacement. So force is different at different places. Force is different at different places. So what we have to take, we have to consider the small minute distance. For that minute distance, what is the work done? So F by Q0 is force per unit charge, which is known as electric field intensity. And this work done should be against the electric field. So we have to put minus here. So dV is equal to minus EdR. And if you want to find V, you have to integrate the entire field. You have to integrate means, so we have to put the limit for R. From where to where we have to do the integration. From where to where we should bring this plus 1 coulomb from somewhere else, from infinity to where, to the point R. So this is the formula for, basic formula for potential difference. And from this formula you can write E also. If you, from this formula you can write E also. E is equal to minus dV by dr. That is the rate of or negative gradient, that is dV by dr is rate of change of potential difference with respect to r, that is dV by dr. That is also known as gradient. The rate of change can be also written as gradient. So negative gradient of potential difference, potential, electric potential, simply speaking. So electric field intensity can be also defined as the negative grade of electric potential, and the unit of electric potential. Unit of electric potential is what? What's the unit of electric potential? It is volt. Electric potential unit. I am speaking about electric potential unit. It is simply volt. Volt. Okay. So from that also, from this, we can decide the unit of electric field intensity. Unit of electric field intensity. So we know the unit for electric field intensity. One is Newton per Coulomb. As per this formula, force per unit charge, right? So for the force, it is Newton. For the charge, it is Coulomb. So Newton per Coulomb. And as per this one, dV by dr. dV is the change in potential difference, that is volt per meter. So we have two units for electric field intensity. One unit is volt per meter and another unit is Newton per Coulomb. Mostly this volt per meter only they represent electric field intensity mostly in the unit of volt per meter in this chapter. Okay, so Newton per Coulomb is also a correct unit. Is that clear? Any doubts on this? No. Okay, I hope you have the notes for this. Now we'll move on to the next topic. Do you have the notes for this? Yes. Okay. Now we are going to derive the electric field intensity. Now we are going to derive the, electric potential due to at a point, electric potential at a particular point. So electric potential at a point due to electric field intensity and due to electric field, due to a point charge, So we're going to derive the formula for electric potential at a particular point due to a point charge. We know that because of that point charge, there is an electric field, and we know the formula for electric field intensity at a particular point. Say example, if we have the charge Q at point O, and at some distance, let P is the point, which is at the distance of R from Q. Okay, so let Q is at O. Okay, let the point charge is Q, which is at O. Now we know the formula for electric field intensity at P. So if we have the charge Q and from a distance, from the R distance, what is the electric field intensity? It is Q by 4 pi epsilon 0 R square. We know that. So the basic thing is what we have to do. We have to bring 1 Coulomb charge here, and we have to calculate the force between this capital Q and 1 Coulomb. So the formula for capital Q and 1 Coulomb is 1 by 4 pi epsilon 0 Q1 Q2. Q1 is 1, Q2 is 1 by the distance R square. So if we find force per unit positive charge, because I am dividing F by Q0. F by Q0 mean I just substitute in terms of instead of Q0, I just substitute 1 Coulomb. So this is what electric field intensity, force per unit positive charge. So only I substitute 1 coulomb here. So the formula is, the basic formula is equal to Q by 4 by epsilon 0 R square. Okay. Now, now what we have to find? We have to find the electric potential at point P. Electric potential at point P. For that, the basic thing is dV is equal to minus EdR. This is the basic formula. From that, if you want to find V at point P, so you have to integrate minus EdR from where to where? From infinity to R. The lower limit should be infinity and the upper limit is the R, because you have to bring 1 coulomb from infinity to this point R. Now, the basic formula for integration, there are many formulas in integration. In that, one of the basic formula is, if you are going to integrate x to the power of something, with respect to x. If you are going to integrate x to the power of something with respect to x, then what you have to do? You have to add 1 with the power, and again you have to subtract the same. You have to subtract, you have to divide the same. You have to divide the x power n plus 1 by the n plus 1. So this is the formula. You should add 1 with this n, and you should divide that n plus 1. You should divide that x to the power of n plus 1 by n plus 1. And in that, if you have the limit a and b, you should put here. If you have the limit, let it be a and b, then you should put here. This means instead of x, first you should substitute b. Then once you substitute b, then you have to put minus, then you should substitute a. This is how the integration should be done. First you should substitute b power n plus 1 by n plus 1 instead of x, because you did integration with respect to x only. So instead of x, you should substitute b. Then after that, instead of x, you should substitute you should substitute a to the power of n plus 1 by n plus 1. So this is how the integration works. Now we have to do the integration of E with respect to R. So what can we do? So minus Q by 4 pi epsilon 0 R square, because E is equal to minus Q by 4 pi epsilon 0 R square dr, and the limit is again minus infinity to R. The next step here, the Q4 pi epsilon 0, these are all the constant thing. So these are all nothing to do with R. So they are not depending on R. So we can simply take out from the integration. So what we have now, 1 by R square, that can be written as R to the power of minus 2, because we want to integrate that, right? So we just write it in the form of x to the power of n. So R to the power of minus 2 dr. The limit is infinity to R. Now minus Q by 4 pi epsilon 0 and R to the power of minus 2, the same formula you can apply. When you did the integration, you shouldn't put this simple. You have to put the bracket like this, closed bracket, R to the power of minus 2 plus 1 by minus 2 plus 1. Then the upper limit should be, lower limit should be written here, and the upper limit should be written here. So I will write the balance thing here. V is equal to minus Q by 4 pi epsilon 0. And this will be R to the power of minus 1 by minus 1. The limit should be infinity to R. Minus 2 plus 1 is minus 1. And you can take this minus 1 outside. So this will be Q by 4 pi epsilon 0, because this minus and this minus is getting cancelled. So R to the power of minus 1 is nothing but 1 by R to the power of 1. So in that only you have to substitute the limit. So if you substitute the limit, upper limit, what do you get? In upper limit, instead of R, you just substitute R. Instead of R, then minus, you should substitute infinity. And we know what is 1 by infinity. Anything when it is divided by infinity, it should be 0. So the final formula is V is equal to Q by 4 pi epsilon 0 R. So here if you take E here means E is inversely proportional to R square. E is the force only, right? So it is simply inversely proportional to the R square as per the Coulomb law. Force is inversely proportional to the square of distance between them. But when you speak about potential difference, it is inversely proportional to just R. It is inversely proportional to just R. V is inversely proportional to R. Okay. Is that clear?
Yes, sir.
Any doubts in the any of this stuff? Okay. So now we have the formula for electric potential. So say if we have a charge Q at here, then when we have the charge at here, if you want to find the electric potential at a point which is at the distance of R from the source charge, because of this charge only we have the electric potential here. So the basic formula is Q by 4 pi epsilon 0 R. If you want to find the electric field intensity, it should be Q by 4 pi epsilon 0 R square. But electric potential means it will be Q by 4 pi epsilon 0 R. So simply you can get this formula. Instead of deriving like this, you can understand the concept of this formula, because V is work done. Work done is force into displacement. Force into displacement. Force means force by unit positive charge. So force into displacement. So force is here electric field intensity only. So if you just multiply this electric field intensity with the displacement R, if you just multiply this electric field intensity with the displacement R, then you will get this. Then this R and R square are getting cancelled. So you will get this formula. So this is the simple way of getting one. But the actual meaning is we can't simply multiply this R. What we have to do, we have to integrate this E with respect to R. Now, if you have the graph between, if we draw the graph between electric field intensity, let it be R here. This is electric field intensity E here. And I just, in y-axis, I use both electric field intensity and potential difference. For both of that, I'm going to draw two graphs. I'm going to draw two graphs. So one is electric field intensity with respect to R. So we know that electric field intensity, it is inversely proportional to R square. It is inversely proportional to R square. So inversely proportional to R square means, let it be, if R is equal to 0 means this electric field intensity is infinity. That's okay. But when the R value is 1 means, when the R value is 1, let it be here, I can put when the R value is 1. So if the R value is 1 means, let it be electric field intensity, let me say some point, let it be 10. Okay, for a sake of convenience, I just argued. If R value is 1 means, let it be 10. If I increase the R value 2 times, what will happen to this 10? If I increase this R value 2 times, electric field intensity should be decreased to 4 times. Am I correct? So it should be 2.25. Somewhere like here. If it is 2, 4, 6, 8 means, if this is 2 means, it should be somewhere like here. So the graph is going like this. The graph is going like this. And if the R value is infinity, again it goes to 0. So this is E versus R. Now I'm going to draw the graph between V and R. V and R. For V also, I can consider the same point. For V also, let me consider E is equal to V is equal to 10. But if I increase If I increase distance for 2 times, V is inversely proportional to just R only. If I increase distance for 2 times, V should decrease 2 times, right? We should decrease 2 times. So it should go somewhere here. So again, that graph also following the same way, but in the different manner, like this. So, but at the same time, if you decrease this one, if you decrease this one to half, if you decrease 2 times means what will happen to this 10? This 10 has increased 10 times, 4 times. If you decrease this 1 to 0.5, then what will happen to E? E will go at 0.5, it go around 40. But at the same time, this should go around 20 only. This should go around 20 only. So this is the graph. So before 1, E dominates. After 1, V dominates. So this is V versus R. So the graph you should have the clear understanding about the graph between E and R. So both are behaving in the same manner, because when R is equal to 0, both are infinity. When R is equal to infinity, both are 0. That's okay. But when R increases, E is decreasing at faster rate compared to V. So is that clear? Is that clear? Any doubts? Okay, so make a note of this. Okay, so now we are going to derive the electric potential due to electric dipole. So what is the electric potential? What is the electric potential at any point due to electric dipole? Due to electric dipole. What is that actually? So we know what is electric dipole. Electric dipole means if you have 2 charges, minus Q and plus Q, separated at some distance. If 2 equal and opposite charges are separated by some distance, then it is called as electric dipole. So in our first chapter, we have derived electric field intensity at the axis of electric dipole. What is the electric field intensity at the axis of electric dipole? What is the electric field intensity at the equatorial line, that is perpendicular at any point that is perpendicular to that is on the perpendicular line of the electric field in the electric dipole. So 2 formulas we have derived. One is electric field intensity due to electric dipole at a point on its axial line. The second one, electric field intensity due to electric dipole at a point on its equatorial line. So both of things we derived. Now we are not going to take axial line or equatorial line. We are going to take the common line. We are going to take a common line from an electric dipole. Any line. You can draw any line from electric dipole. In that line, you have to find the electric potential. In that line, you have to find the electric potential. Is that clear? Now, for this question, the diagram should be very important because we have 2 charges. One is a minus Q and another one is plus Q. Okay, another one is plus Q. Now we know that both are separated at the distance of So we know that both are separated by some distance. So basically we denote the distance. Basically, we should make the center point. We should make the center point and let it be O, and the minus Q is at point A. Minus Q should be put on first, then plus Q we have to put plus Q. So plus Q is at B. Normally we take the distance between these two charges, or the length of the dipole normally is taken as 2a only. Normally 2a only, because from A to O it is 1a, and another O to B it is another a. From center to center we took the distance a and a, so the total distance should be 2a. So these are all very known things to us. Now in the previous chapter we take 2 points. One is at the axial line, so any point at here, and another one is at the equatorial line. So we found electric field intensity on these 2 points. Now the point we can take anywhere that is surrounding to the electric dipole. You can take anywhere. So you need not to take point on axial line, and you need not to take point on the equatorial line. You just take the common point. So what you have to do, you have to draw the line between O and the point you want to find electric field intensity. So let the point is P. So let point P is at the distance of R from center of electric dipole. So basically we take the distance from the center of electric dipole only. So that distance should be taken as R, center of electric dipole. Okay. Now the purpose is we have to find the electric potential due to these two charges at point P. Okay. So for that, say example, if I want to find electric potential at P due to minus Q. So let me take that as V1. So I know the formula for electric potential. Electric potential formula is Q by 4 pi epsilon 0 R. This is the formula for electric potential. Now if I have minus Q means the electric potential I can take it as V1, but V1 is equal to Q by Q. Here is negative charge, minus Q by 4 pi epsilon 0. The distance between A and P we should take, because we take the distance between O and P only. So let me consider the distance between A and P as R1. Let me consider the distance between A and P is R1. So it is 4 pi epsilon 0 R1. When we write the electric field intensity, we shouldn't mention plus or minus, because in electric field intensity we always mention the direction, whether it can be attracted or repelled, at which direction the force will be. The direction we always mention, but this electric potential is the force. This electric potential is the work done. Work done means it is the energy. So when you write the energy, or when you write the any scalar quantity, energy is the scalar quantity, right? So this potential is basically a scalar quantity. When you write the scalar quantity, you can't mention the direction. You can't say whether it is attracted or repelled. Whatever you can say, this energy is required to bring 1 coulomb charge from infinity to this point. That's what we can explain. So If the charge is negative means, automatically, if the source charge is negative means, automatically this minus q itself can attract 1 coulomb to point P. If we just bring plus 1 coulomb means, bring 1 coulomb means, we need not to do any work. This minus q itself can do the attraction. So here the work is done by the charge. It is not done by us. It is not required to done from the external source, because here if we have minus q means basically attraction happens. So we should mention that minus q. But in force, if we are writing, we should mention the direction. According to the direction, it is a final answer we have to find. So this is the energy means. So since this is the energy, so we just need to mention this energy should be done externally, or it can be done by itself. It can be done by itself. So we have to put, we don't need to give any energy. So we just put minus q. And in the same way, electric potential due to plus q. Electric potential due to plus q. Electric potential at point P due to plus q. Let it be V2. So for plus q, I should take the distance. I should take the distance from point P to capital P. Okay. So this is the distance. Now this distance I can written as R2. This distance I can written as R2. So this, since this is the plus q, there will be a repulsive force, so that we have to do the work from the external source. We have to do the work from the external source. So what we can put? We can put plus q here. So the work is the positive here because it is done by us. So 4 pi epsilon 0 R2. When in the case of electric field intensity, we have two different directions. We have to find the, because of the force in two different directions, we have to find the resultant force. So we have to find the components of the force, or we have to find the horizontal and vertical. The resultant means we have to resolve the force, right? We have to resolve the force. We can't simply add. If the two forces are in the same direction, either we can add or subtract it. If the two forces are in different direction, then we should resolve that. So here it is not the case. Here V1 is the energy, V2 is the energy. So V1, so if you want to find the total electric potential or net electric potential, let it be net electric potential at point P. If you want to find the net electric potential at point P, what do you need to do? You can simply add that energy. You can simply add that, because this is the work done by the system itself. This is the work done by the external one. So the net potential should be V1 plus V2 only. So you can simply add that. You don't need to consider any direction because it is the scalar quantity. Hope you get my point. So V is equal to V1. We know that minus Q by 4 pi epsilon 0 R1. And V2 is equal to plus Q by 4 pi epsilon 0 R2. So I can write net potential here. V is equal to, in these two terms, I can take Q 4 pi epsilon 0 are common. So this 1 by R2 is positive. Then this minus 1 by R1, we can take it on We can take it as the negative. So 1 by R2 minus 1 by R1. So now this is the formula for net electric potential at point P. Is that clear? Any doubts on this? Okay, but we are not done here. We should represent this V in terms of R1V. We don't have the values of R1 and R2. For our calculation, for our formula application, we take this R1 and R2. But basically what they gave, see, this is my electric dipole. In that electric dipole, I want to find the electric potential at point P, which is at some distance from center of the electric dipole. This R only they gave. So the formula should be in terms of R only. It should not be written in the final version should not be written as R1 and R2. Do you get my point? We can't write the final version in terms of R1 and R2. It should be written in terms of R. So what we have to do, we have to represent this R. We have to represent this R1 and R2 in terms of R. Okay. To represent this, to represent R1 and R2 in terms of R, first we know that this point P is at the distance of R from O. This information is not only enough. The another information we need is at how much angle this line is. Because at R distance we can draw too many points. This is also at R distance only, and we can write too many points. Like if this is this point is at the same R distance. If I draw here, this is also at the same R distance. This is also at the same R distance. So this line, that means that at R distance, we can draw many lines. So if I want to mention, if I want to find at this particular point, the angle I should know. That angle I can consider that as theta. Now, the thing is, we have to represent this R1, R2 in terms of R. For that, in a triangle, because we have two triangles here. One is OAP, one is OAP. So this is A, this is R, this is R1. And this angle only is theta. Actually, the entire angle on the line will be 180 degree. Normally, the total angle in the line will be 180 degree. So this angle must be 180 minus theta. In triangle, if we know two sides at one angle, we can easily find the another angle. Or if we know the two sides, so this side is R, this side is A, angle between this R and A is 180 minus theta. From these three terms, we can write R1 by using the formula called cosine formula. What is that formula? Cosine formula. The formula is R1 square is equal to R square plus A square, minus 2AR cos, what is the theta here? 180 minus theta. Do you get the formula? R square plus A square minus 2AR cos 180 minus theta. Is that clear? Yes. Now, the cos 180 minus theta means the angle will be in second quadrant. Cos 180 minus theta means the angle will be in second quadrant. In second quadrant, if you write the cos, that will be negative. So instead of cos 180 minus theta, you can just write minus cos theta. So R1 square is equal to R square plus A square minus, so this minus cos 180 minus theta, basically minus, so it will be plus cos theta plus 2AR cos theta. Is it clear? Instead of cos 180 minus theta, I am substituting minus cos theta, so this will be plus 2AR cos theta. And similarly, we can write R2 here. R2 we know, A we know, I'm sorry, here. R we know, A we know, angle between these two things also we know. Now from that we can represent this R2. We shouldn't use the Pythagoras theorem because it is not the normal triangle. There is some angle, right? So we know the angle between R and A at theta. So we can write R2 is equal to R square plus A square minus 2AR cos 180 minus theta. Here we put, here simply cos theta only we should put. No, it is not parallelogram theory. Maybe we can use that one also. It's from parallel. If you write in the form of vector, then the derivation of this one is from the parallelogram derivation only. Okay, so like a parallelogram also we can write. In triangle, if you know two sides and one angle, we can write the third side. So that's the thing. If we know length of two sides and one angle, we can write the third side. Okay, is that clear? Okay, now things are not over here. We know R1 square and R2 square, but what we need to find is, we need to find 1 by R2 and 1 by R1. That's the thing, right? So because in this formula we are having 1 by R2 and 1 by R1, so I'm trying to find 1 by R2 minus 1 by R1. I'm trying to find 1 by R2 minus 1 by R1. So I know that R1 square is equal to R square plus A square plus 2AR cos theta. So from this, just take R square as common. R square as common from all these three things. Just to take R square as common. Why? Because in the next step I have to inverse this. So before I'm going to inverse this, I just take R square as common. That means if I take R square from this value, it will be 1. Here it doesn't have any R square. So if I take R square as common, means you should divide by R square. And this term consists have only R. So if you take R from this, R square from this, you need to divide by R. Is that clear? Is that clear? Is it clear or not? Okay. Now, when you compare the value of A is the distance between the dipole. A is the distance between the dipole, and R is the distance of the point from the dipole. So I already told that the dipole, we draw this dipole in a large manner for our understanding. Okay, for better view. Basically, the dipole, the length, the distance between two dipole will be in very low, low distance only. It is in terms of 10 to the power of minus 10, minus 9. That much amount, it is low, because it represents the molecule size. It represents the molecule size. Basically, we have H plus and OH minus. That is the dipole. Okay, HCl means H plus and Cl minus. That is the dipole. So you can compare the size of the molecule. So the distance between the the distance in the dipole is basically, it is in the size of molecule. So the A value, practically speaking, A value should be very, very, very less than R. And if you square it again, it will be more or less. So when you divide A square by R square, it will be very low, because you are dividing a small value with large value. So what you will get? You will get 0.00 something only. So it is nearly equal to 0. So since a square is very lower than the r square, we can a square and by r square is negligible. Okay, can be neglected. So r1 square is equal to r square plus 1 plus 1 plus 2a cos theta by r. Okay, now inverse this because I want to find 1 by r1. So if I inverse this, I need to inverse this r square. If I inverse this, I can put -1 here. 1 plus 2a cos theta by r whole to the power of -1. Am I correct? So it is 1 by r square. When you write the formula like this, when you have formula like this, 1 plus x whole to the power of -1, that is binomial expansion. You can use the formula called binomial expansion when you have the formula like this, 1 plus x power -1. That is 1 minus x plus x square minus x cube, etc. It goes on. 1 minus x plus x square, okay, etc. It goes on. So basically you can neglect this x square x cube terms because here it is 2a cos theta by r, right? If you square it, means it will be again a square by r square. That can be neglected. So what we can put, we can get these two terms only. So expand the above formula, expand the above term by using binomial expansion and neglect the higher orders Is that clear? Okay. So if we do that, then we have first two terms only. First term is 1. Now this -1, actually what will happen, this -1 is multiplied by this x, then only this will become minus 2a cos theta by r. Okay, actually before this we can do this. Before this, just find the square root. After that, do the expansion. Just find the square root. Okay, if you find the square root, then 1 by r1. For this, if you take the square root, this will be 1 by r. For this, if you take the square root, this will be minus 1 by 2. Because if you take the square root, then the power should be 1 by 2. So here you are having already -1. This will be minus 1 by 2. Is that clear? Now you can do the expansion. So it is 1 minus 1 plus x whole to the power of n. 1 plus x whole to the power of n. So in that, basically what you will get, the first two terms will be 1 plus nx, like that it goes on. Then x square x cube terms will come, that we neglect. So first two term will be 1 and this n is multiplied by this factor. So 1 by r1 is equal to 1 by r1 is equal to 1 by r1 is equal to 1 by r. This minus 1 by 2 is getting multiplied by this 2a cos theta by r. So 1 plus minus 1 by 2 into 2a cos theta by r. So 1 by r1 is equal to 1 by r1 is equal to 1 by r into this 2. If those two are getting cancelled, then 1 minus 2a cos theta by r. Is that clear now? Okay. Now, in the same way, we have to find 1 by R2. We have to find the 1 by R2. So for that, the same derivation only we should do. So now to find, now we have R2 square. R2 square is equal to R square, sorry, R square plus A square. Here you are having minus 2AR cos theta plus 2AR cos theta. In here you are having minus 2AR cos theta. So what makes the difference? The find this minus one thing. So we can directly write the final formula from here. 1 by R2 is equal to 1 by R, the same thing, 1 by R. Here 1 minus is there, right? So here 1 plus should be there. 1 plus 2A cos theta. Sorry, this 2 is getting cancelled, right? So it is 1 plus A cos theta by R. Okay. 1 plus A cos theta by R. So what is actually we need to find? What's the thing actually we need to find? We need to find 1 by R2 minus 1 by R1. So now we have formula Q by 4 pi epsilon 0. Instead of 1 by R2, I put this 1 by R plus 1 plus A cos theta by R. Minus, instead of 1 by R1, I put this 1 by R, 1 minus A cos theta by R. Is that clear? Now, in these two terms, I can take 1 by R as common. So Q by 4 pi epsilon 0. Here is also I'm having R. Here is also I have R. So I just took this R. So it is 1 plus A cos theta by R minus 1 minus A cos theta by R. So 1 plus A cos theta by R minus 1 plus A cos theta by R. Is that clear? If I take this minus 2 bracket, minus 1 plus A cos theta by R. So 1 and minus 1 is getting cancelled. A cos theta by R, A cos theta by R. It is V is equal to Q by 4 pi epsilon 0 R. A cos theta by R, A cos theta by R. So what is that? It is 2A cos theta by R. Am I correct? Am I correct? So what is 2QA cos theta by 4 pi epsilon 0 R square? 2QA cos theta by 4 pi epsilon 0 R square. We know what is 2QA. In a dipole, the dipole moment here, when you write the dipole moment is fixed. Dipole moment is charge into distance between them. Any one of the charge in distance between them. So Q into 2A is the dipole moment. So 2QA is the dipole moment, which is P. So P cos theta by 4 pi epsilon 0 R square. So this is the formula for electric potential due to electric dipole at electric potential due to electric dipole at any point, at a distance, at a point which is at the distance R from the center of the dipole. Formula is P cos theta by 4 pi epsilon 0 R square. Is that clear? See, in electric field intensity, you have the formula like this, either 2P by 4 pi epsilon 0 R cube. In electric field intensity, when you find the electric field intensity at the axial line and equatorial line, the formula is like this, 2P by 4 pi epsilon 0 R cube and P by 4 pi epsilon 0 R cube. Like that, you have two formula. But here, P cos theta, the angle also you should take, because you are not taking axial line or equatorial line. You are taking some point, so which is at some angle. So you should take P cos theta and 4 pi epsilon 0. Here you should take R square. In electric field intensity, you have R cube. Here you have R square. So you can compare these two formulas. Is that clear? Okay. So just make a note of this. In next class, we will be having some special cases from this formula. After that, if you have too many charges, what is the electric potential and how to find the potential energy of the system, how to find the potential and electric potential energy of the system. Okay, so with that, the first half of the chapter will be over. Then we can move on to the second half, that is thing, the concept of capacitance will be the second half. Okay. Just make a note of